ความเป็นคนจะก้าวเดินไปด้วยใจองอาจตามรอยพระบาทของพ่อไม่ย่อท้อไม่หวั่นไหวจะขอเป็นคนดีเป็นลูกที่ดีของพ่อศักดิ์ศรีของมอ.จะขอเทิดทูนตลอดไปยึดมั่นคุณธรรมตราบที่ยังมีลมหายใจจดจำไว้ว่าความดีคือศักดิ์ศรีของความเป็นคนไม่มีที่ไหนที่เราภาคภูมิใจกว่านี้เมื่อได้อยู่ใต้บารมีสมเด็จพระราชบิดา
จะขอเธอทูลนามพระราชทานตราบนานแสนนานจนกว่าสิ้นดินฟ้าสิ้นลมหายใจ
จาก50 ปีที่ภาคภูมิใจจะก้าวต่อไปสู่วันข้างหน้าด้วยความรักความศรัทธาไม่เคยเสื่อมคลาย
Okay. Bismillah. Just starting in a couple of seconds. Okay. So, Assalamu alaikum and good day. Chair panel, presenters, audience, and everyone. Welcome to the parallel session of Engineering and Natural Sciences, Room 9, hosted by our fellow Prince of Songkla University. I, Bakr Saleh, joined by Farida, are your BIC and moderators for today's session. So, my partner will send the registration form in the chat box provided. So please don't forget to register. So I may start to introduce the chairman of the session. Please help me in welcoming Prof. Dr. Sansuri, Sansuri, an associate professor from 2018 till now, at the Prince of Songkla University, Thailand. Joined by the co-chairs, Associate Prof. Dr. Wan Zoha, a senior lecturer at the Faculty of Engineering, University Putra, Malaysia, as well as Associate Prof. Dr. Wan Nur Hayati, Associate Professor at the Faculty of Computer Sciences and IT University Putra, Malaysia. Last but not least, Associate Prof. Dr. Sawal Hamid Muhammad Ali, Chairperson of Department of Electrical and Electronic and Systems Engineering at the Uni of Kebangsaan, Malaysia. Without further ado, we will start today by presenting the rundown slideshow. So this is our schedule for today. So we start with COVID-19 title and COVID-19 and pneumonia detection system using deep learning with chest X-ray images. So now let's start the presentation.
Hello, ladies and gentlemen. My name is Mohammad Afik, and I'm from University Technology Brunei. I'm representing all my collaborators to deliver our presentation about COVID-19 and pneumonia detection system using deep learning with chest X-ray images. The following is the outline of my presentation. I will start with a brief introduction about the research, including the background and objectives. Then I will explain the methodology that we use and continue with presenting the results and our analysis. I will then close my presentation by giving some concluding remarks. I am sure everyone here is aware of COVID-19 disease. I suppose it is the one of the reasons why we are presenting in this conference. It has been around 1.5 years that the world is being gripped by the COVID-19 pandemic. While understanding about the disease has improved and some vaccines have been invented and applied to public, the variant of the virus keeps evolving and some of them are getting harmful. The symptoms of COVID-19 infection range from nothing to severe. In severe cases, the virus affects lungs, giving similar symptoms like pneumonia, which is quite common lung infection in countries in the Southeast Asia region caused by either virus or bacteria. Severe cases of either COVID-19 or pneumonia could cause fatality, thus fast diagnosis and immediate also safer as it is easier to sanitize the equipment after each use. The picture on the slide shows some samples of chest X-ray, which I suppose most of us has experienced having one. While COVID-19 vaccination programs have been driven globally, as mentioned before, the pandemic situation is not getting better yet. Infection is still thrive. Even worse, currently countries in Southeast Asia have the center of the pandemic. As we seen in the table shown, on 24th July, 6 out of 10 Asian countries are among the top 15 for the daily infections. Hundreds or even more than 1,000 people dies in a day due to the infection. That this most likely is due to severe cases. Currently, the Delta variant of the virus are dominating those cases, and this variant attacked the patient's lungs quite severely, which results in death within few days. Or also often the patients die due to lungs failure after they were declared COVID-19 negative and thought to have been recovered. While fast diagnosis and immediate treatment are needed, these Southeast Asian countries don't have enough radiologists to handle the huge number of cases. Therefore, an automated assistive system is needed, which motivates this research. So, the objective. Hello, ladies and gentlemen. My name is Mohammad Afik, and I'm from University Technology. Use either X-ray, CT scan, or MRI samples of chest or the pandemic. The center or severely a huge number of COVID-19 system, deep and abstracted and image classification. There is a specific architecture of neural network was implemented called convolutional neural network. It is a deep learning algorithm which can take in an input image, assign importance such as learnable weights and biases to various aspects and objects in the image and be able to differentiate one from the other. There were many architectures in convolutional network for fine-tuning the neural network layers, and each of it has different accuracy level. From earlier research, VG16 gave high accuracy compared to other models. Therefore, this project proposed to use VG16 for the trained model. It contains 16 layers that has default input size of 224 times 224 pixels with 3 channels for RGB image. Model from scratch means that the layers are fresh and never learned with any data before. Then a pretend model is a model created by someone else to solve a similar problem. Instead of building a model from scratch to solve a similar problem, you use the model trained on other problem as a starting point. For example, if you want to build a self-driving car. While the pretend model was trained with nature images only, not chest X-ray, many researchers are still using the model for medical images. The procedure for the chest X-ray identification followed this methodology. A set of chest X-ray images comprising the COVID, pneumonia, and normal chest X-ray are collected to create the dataset for training and testing. Then, convolutional neural network algorithm is used to train the model to be able to identify those images. In this case, we use VG16. Optimizer and loss and activation function are used also in the deep learning process. Performance is then evaluated to determine whether the model used can identify and classify the chest X-ray in the testing and datasets correctly. If the performance is high enough, then the system can be used to make the prediction of any chest X-ray to get correct prediction of either the chest X-ray is COVID-19, pneumonia, or normal chest X-ray. We use the following configuration for the procedure. The left table is showing the number of images that is used in the datasets for the training and also for the testing. And then the right side of table, the parameters used in the procedure are listed. We use Python to run the algorithm and the procedure. After the model is determined and the deep learning procedure using VGG16, including the training and validations are executed, we obtain the results as shown in this slide. For the VG16 model from scratch, the results are pretty good with quite high accuracy, although as you can see in the confusion matrix that the number of predictions are lower than the number of images in the datasets that are used for the testing as shown in the table before. To improve the result, we use preprocessing technique. The preprocessing is applied to the chest X-ray images by converting the images to BGR from the normal RGB state, as well as the color channel is zero-centered. This preprocessing improves the result, as you can see from the value in the diagonal elements of the confusion matrix, which are closer to the number of the images used for the testing. This means that more images are identified and classified correctly. To improve more the accuracy, a pre-trained model is used. This pre-trained model is a VGG16 model that has been trained using image datasets from other applications. As seen on the slides, both from the accuracy graph and the confusion matrix, this pre-trained model applied to the chest X-ray dataset performs better, although the model was previously trained with other natural images, which includes animal. The training accuracy graph shows that the accuracy for training and validating are increasing. Then, the training and validating losses are decreasing. Close to all images in the test datasets are identified correctly. From the training and the test, we have seen that the pre-trained model performs better compared to the other two methods, which is using VG16 from scratch and the use of preprocessed function. Then we use the model to predict input chest X-ray images, and we obtain consistent results. The 5 chest X-ray images on the top row show the prediction using the VG16 from scratch, where 2 images are predicted wrong. Those 2 images have been distorted with rotation and adding noises. While they are actually COVID-19 chest X-ray, they are identified as normal instead. The bottom row are the prediction result using pre-trained model. It shows that the pretend VG16 model can correctly predict all 5 chest X-ray even when the chest X-ray images are distorted. We also built a simple graphical user interface GUI so that it is easier for users such as radiologists or other hospital workers to operate the system. The GUI only requires 2 buttons: to upload the image and to classify which classes it belongs to, as you can see from the picture above. To implement the system in an embedded hardware, a Jetson Nano 2GB microprocessor was used. This processor is basically a small computer that needs 5-volt power supply with 3 amps current, including mouse and keyboard. The Jetson Nano is chosen as it is an inexpensive, small in size, which means portable, while it is quite powerful. However, Jetson Nano 2GB could only run the simplified version of the system, in which the model needs to be optimized further with less layers. For real implementation, a higher specs microprocessor with also larger memory capacity needs to be used, while it keeps the cost low. To sum up everything, we have studied the image-based deep learning to detect COVID-19 and pneumonia. Then, using VGG16, we obtained quite highly accurate prediction results of both diseases in the chest X-ray images. We have also built a simple GUI and embedded system to implement this detection system using Jetson Nano, although further development is needed. This study provides promising results that are potentially useful in helping health workers and patients to tackle short and long-term effects of COVID-19 pandemic in Asia and beyond. Thank you very much. Hello, ladies and
All right, we thank Mr. Afiq for the presentation. Now for the Q&A session, if there is any.
Any question from the floor? Okay, I have just one quick question though. Do you have, can you tell me the difference between the X-ray chest image between the COVID-19 and pneumonia? It seems like it's very similar though. Do you have any suggestion or any information on that?
Sorry, we don't have really information about that, but what I can share you is that pneumonia and COVID-19 have same symptom, where it has glass. It has features like a white vein inside the chest X-ray, which is hard to determine which X-ray is pneumonia and COVID-19. That is all.
But on the data set that you use, you have both, right? The COVID-19 and the pneumonia.
Yeah.
To train the model.
Yeah.
So
if I may help a bit to answer that question. Okay. So
yes,
yeah,
please.
By the look, I mean, if you are not an expert, just by looking at the X-ray, we cannot really distinguish. But for the radiologists, they can, because like the data set that we use is taken from like a standard data set.
The internet.
Yeah. So that's already like specified that this is pneumonia and this is COVID and the other sets are normal. So that's already verified. But we as non-expert cannot distinguish, but the expert can. So that's why we need the expert system, the deep learning systems to help us to detect correctly.
And also I want to add too that I downloaded it from the internet, and it already divided into 3 folders, which is pneumonia, COVID-19, and also normal chest X-ray.
So have you compared your result with other papers result at all? Do they have how
it's actually our
doing?
actually we this is my final year paper, and we did literature reviews with other research. We did literature review, and we also read some of other researchers, and the differences is that the confusion metrics and also the percentage, the performance metrics. I'm using VG16. Other researchers are using different layers too, such as Inception, MobileNet, and so on. And we managed to get 90% above, which is good already.
So what will be your next step then? You're gonna improve it or try to use it on the field test or something?
For now, what we're liking is that the implementation using Jetson Nano 2GB is not working actually with the use of our actual model. So our next step is basically to use the Jetson Nano and to implement simplify layers so that it can work in the hardware, which is Jetson Nano 2GB.
Yeah, we have two options. Either use the Nano, simplify our algorithms to be able to use it with the Jetson Nano 2GB, or we can use our model, but we need to use a more powerful processor. And that's the next step that we are planning to do.
Very good work. Yeah, thank you very much. I have no further question. Thank you. Any other questions? Do we still have time? No. Okay, we still have about 1 minute. Do anyone has any more questions? Any co-chair want to ask any question? Thank you. Okay. I think, thank you very much. Very interesting work, and hope you get the result better and better. Thank you.
You're welcome. Thank you very much.
All right, Prof. Should we proceed with the next presentation?
Do we still have time or? Time's done.
มีเวลาไหมเมื่อกี้มี30 วิ
Proceed to the next one, Mr. Baker. Thank you. Yes.
Thank you.
Good morning to all.
So now we will proceed with the next presentation. For that, I would like to invite our presenter, Morogaya, I believe, for the paper of identification of COVID-19 infected individuals using cough sounds.
Good morning to all. I'm Murugaya Ramashini from the Faculty of Integrated Technologies, University Brunei Darussalam. Today I'm here to present our research titled Identification of COVID-19 infected individuals using cough sounds. Today my presentation will be arranged in this manner, where the introduction and aims and objectives of this research will be presented first. Then, the scope of the research will be briefed. After that, the proposed methodology will be elaborated. Later, the key findings of the research will be presented, followed by the conclusions and future works. As we all know, COVID-19 is an illness caused by the novel coronavirus. This virus infected over 170 million people and caused over 3 million deaths worldwide. The novel coronavirus can spread from one person to another easily when an infected person coughs or sneezes. Hence, it is essential to develop methods to effectively and accurately detect COVID-19 infected persons to limit the spread of the virus. The vocal sounds, including cough sounds, may be considered as accurate source that can be utilized to obtain a variety of health information used for diagnosis purposes for the early detection of coronavirus infected persons. Thus, this research work introduces an audio signal processing based application that can be classified COVID-19 infected and healthy individuals through their cough sounds. Therefore, the main aim and objective of this work are to provide an audio signal processing based application to identify COVID-19 infected individuals using cough sounds, and also to explore the most suitable audio features to classify COVID-19 infected and healthy individuals through their cough sounds. To inline with the aim and objectives, the scope of our work focused more on analyzing the cough sounds of both COVID-19 positive features are extracted from cough sounds to find the most suitable septal features. Finally, the performance of the supervised ensemble bagged tree classifier is evaluated with 3 different models. The proposed methodology consists of 3 main stages: data collection, feature extraction, and feature classification. The cough sound data has been collected from open source online available data sources and separated into training and testing data sets before being used in the feature extraction process. In this case, we extracted both MFCC and GTCC features separately from cough sounds. Later, the extracted MFCC and GTCC features are fed into a classification model. For training the classifier during the training phase and then to predict whether an unknown cough sounds comes for healthy or COVID-19 infected individuals during testing. Cough sound data inputs were collected from the Coursera data GitHub repository, which comes from a data collection project by the Indian Institute of Science. This dataset includes cough sounds of both healthy and COVID-19 individuals collected between January to May 2021. The selected data set is clear and well processed. Hence, it does not need additional pre-processing before usage. The data set has been divided into training and testing. Separate features are the most prevalent features extracted from speech signals in recognition-related applications. Even though several separate feature extraction methods are available, the MFCC and GTCC are the 2 most well-known methods when considering human vocal sound related applications. Therefore, in this work, we extracted 13 coefficients of both MFCC and GTCC features from cough sounds separately. This figure illustrates the feature extraction process of MFCC as well as GTCC. After feature extraction phase, The proposed ensemble bag tree classification model has been trained and tested using the extracted MFCC and GTCC features separately to give three models. Model 1, which utilizes MFCC features only. Model 2, which utilizes GTCC features only. Model 3, which utilizes combined MFCC and GTCC features as inputs. These confusion matrices shows the overall accuracy of all three models, where Model 1 accuracy is 81.3%, Model 2 accuracy is 75%, and Model 3 accuracy is 87.5%. When considering the first two models, the classification accuracy using only the GTCC features surpasses the classification accuracy using only the MFCC features. Also, Model 1 has correctly classified 13 test inputs out of 16, and Model 2 correctly classifies 12. The overall accuracy of Model 3 using the combined GTCC and MFCC features was higher than the Model 1 and 2. In order to analyze in depth, the results of each test sample were summarized in this table. We can see that Model 1 and Model 2 incorrectly classified the same COVID-19 test sample, but misclassified different healthy cough sounds. Thus, both MFCC and GTCC features were combined to train and test the classification model to derive the benefits from both sets of extracted features. However, combining both GTCC and MFCC features as input to the classification model only improved the classification results of healthy class. In fact, all three models did not manage to classify COVID test sample 6 and healthy test sample 1. Sensitivity, specificity, precision, F1 score, and accuracy values for all three models are given in this table. The sensitivities of all three models are 87.5%, which shows that all three models are equally able to identify COVID-19 test samples from cough sounds. Also, Model 3 using the combined MFCC and GTCC features gives the highest specificity, precision, F1 score, and accuracy. Results from the proposed classification model have proven that the extracted MFCC and GTCC features of cough sounds can be used to classify healthy and COVID-19 individuals more effectively. The overall testing accuracy of GTCC surpassed MFCC feature-based classification. However, the model which utilizes both the GTCC and MFCC features is capable of improving the accuracy even further. I would like to conclude that the best accuracy and precision of 87.5% have been reported using an ensemble bag tree classification model with combined MFCC and GTCC features as input. Further, the proposed classification method can be made more robust by using more training data and adding additional acoustic features together with the proposed MFCC and GTCC features. Also, to make the system more applicable, a real-time cough detection system integrated with hardware implementations can be implemented to assist health professionals in diagnosing COVID-19 infected individuals. Thank you.
Right. For now, I would like to invite the presenter for the Q&A session.
Hello.
Okay, thank you very much. It's very interesting works. Actually, we have the question from the chat box. It's from UTM Diana Berry. She said that it's a very interesting work. Could you explain a bit more about the MFCC and GTCC? Why do you use those two features for the detection? What about comparing other type of disease that can coughing as a symptom too? Thank you.
Yeah. So actually MFCC and GTCC features belongs to septal features, audio-based feature. There are several types of audio-based features like time domain features, frequency domain features, and septal features. So these two features belongs to septal features. And also the difference between this MFCC and GTCC is like MFCC means MEL frequency septal coefficients. So here the MEL scale means it is a measure of pitch, right? So the pitch, it's based on pitch. They are calculating this MFCC feature. And the GTCC feature is actually the feature filter is designed to simulate the process of human audiosity. So based on human audiosity, they are developing this filter. So these two filters are most used in all speech recognition related application. That too, MFCC is the most famous one. And also in all related work, we identified most of the people used MFCC and achieved around 80% accuracy in this work. So we thought of comparing the results, which is GTCC, where one of the main disadvantages of MFCC is its sensitivity to addictive noises. That is the most main disadvantage of MFCC features, where other people use in their work. So we tried to give the better results, whether it's giving the better results with the GTCC, where it's known for robust in noisy environment also. So therefore we checked both the features, and then we got an idea that GTCC gave better results than the MFCC. When we try to combine both the features and test our model, that time it gives more robust, more reliable results. So we are thinking that MFCC and GTCC, from our results, we can conclude that MFCC and GTCC to combine give more accurate results. And also the next second part of the question is about comparing the other diseases which giving symptoms as cough. Yes, of course, we can use it. When we do our literature review, we found some people used to find out different voice pathologies, to identify different pathologies through this method, MFCC and other audio signal processing approaches. So it can be possible. Yeah.
Thank you very much. Are there any other questions? One curious question.
Yeah.
Yeah. You said that the acoustic can be used to improve your works, right? Can you explain more on that?
Yeah. This acoustic features, there are several features. In this, we use the septal feature. So we can include more acoustic features like time domain and frequency domain, even like spectrogram features, in order to improve this application furthermore.
Okay, interesting work. We have about 30 seconds. Have you compared your work, the result, with others that they have done similarly? How was it? Yeah.
There was a work related to this COVID cough sound, and they used only MFCC features, and they achieved nearly 80% of accuracy. So that's how we got to know. We found the MFCC features from there, and we added a new feature like GTCC, and we compared that with their work. And we also got, for MFCC, we also got around 81%, and then for 75%, but for GTCC we got 81%, and then when we compare both the features, we got 87%. So we think compared to their model, we demonstrated that our work produces more accurate results.
Okay, thank you very much.
Thank you.
All right, Prof. So is that all, Prof, for the Q&A?
Yes, the Q&A is done, Mr. Becker. Yeah.
All right. So now, since we have just a second. So now I would like to invite if there is any presenters that would like to do a live presentation, because we have only received 2 videos from the presenters. So if there are any presenters now that would like to present, please show yourself, please. If there are not any, then we proceed with closing the session.
Okay, so are there any presenter in the room that want to present live? I saw a few that come in. If you are the presenter of any papers in this session, want to present live, please identify yourself now, because Mr. Becker informed me that we only have 2 video presenters that sent to us. So if no one, we're gonna move to the closing, which means the photo section, like Mr. Becker.
Yes.
Yeah, and then we're gonna close the session. So if you are the presenters and enter the room, please identify yourself to the staff. Okay, Mr. Becker, I think we don't have, so you can proceed with the schedule. Thank you.
All right, thank you.
Excuse me, what about if other speaker come on their time? I mean, I also didn't see other slides, but what about if they come on their exact time?
Because I was informed that they're gonna enter and they're supposed to submit the videos. If they want to present live, they have to identify the organizers. And Mr. Becker is the one moderator from the organizers. That's what they told us yesterday on the procedure. So
all right, yeah, that's fine.
Yeah, that's why I don't know too. Yeah, but I know what you mean.
Sorry, yes, because we have so many presenters that did not confirm or cancel in the first slot and the second slot. So we have a big time gap. So I'm not sure how to act about this. So we thought to bring presenters forward.
Yeah. All right, it's okay. Maybe we can join other rooms probably.
The Prof, I'm not sure how to act upon this. So.
Well, from Mr. David informed me yesterday is that we moved the presenter up, right? And I don't know because they not show up. Just a second then.
So if you would like, Prof, maybe we can take a break and then wait for the presenters if you would like. If you would like me to go ahead with the closing the session, I would.
Maybe we can take a group photo first, and then I will try to see, contact Mr. David, what to do next, since the presenter is not showing up. So maybe we can take a group photo first for now.
Sure, sure.
How about that?
Sure.
Okay, yeah, okay.
So, Freda, please, can you go ahead and notify us?
Sure can. I'm ready. You can count. Okay.
So I invite all the participants, if you can, please turn on your camera so that the organizer will take a group photo of this session. Okay? Just turn on your camera so that the organizer can take a group photos. Thank you very much. Yeah, I give you a few more minutes so that you can turn on your camera. And I'm not sure who's gonna be the one taking the photo, Mr. Beckers.
Yes, my partner will take the photo.
Okay, so if you can, you have a camera, I invite you to turn on your camera so that the organizer can take a good photo. Okay. And I think we have to take it how many times? I don't know. 3 probably, 3 or 4. How many pages you need to take?
3.
3, okay. Okay, now everyone, I don't know, with mask or without mask, just smile, okay? Okay, 1, 2, 3 for page 1. Okay, next. 1, 2, 3, page 2. Okay, next. 1, 2, 3, page 3. Okay, are we all done? Yeah, I think so. Okay, thank you very much. So, how about we take about like 5-minute break? Let me go see what Mr. David want us to do. Okay, is that okay, Miss Diana?
Yes, thank you, sir.
Yeah, just a second. I know a lot of interesting papers. I want to hear it too. So let me go get the answer for you. Okay, thank you.
Thank you. It's all right. Thank you.
I saw Professor Echo
60
Hello
ตอนนี้60คนเลยนะโอเค not bad
Yes, Prof. Sang. Is everything
Hi
okay?
how are you
Yes, fine.
We are
So-
waiting for the presenter
Oh, okay.
We have only to show up today so yeah
Okay.
How about another room
I just saw that other room still active.
Oh good
Yeah.
nice
They're
yeah
presenting, yeah. Here you have the PIC. Oh, PIC is Becker, yeah.
Yeah
Hello, Becker.
Yes, hello, Prof.
Okay, and how is the next presenter?
I'm not quite sure, but the videos we have the received, we have done.
Okay.
So now I think the next presenter